start. Today, we're going to talk about what happens when a chemical equilibrium system is disturbed and how we can predict the response using a rule called Le Chateliers Principle. In a chemical reaction, at equilibrium, the forward and reverse reactions are occurring at the same rate, and the concentrations of reactants and products remain constant. But what happens when something in the system changes? For example, what if we had a reactant or remove some product? To answer this, we use Le Chateliers Principle. Go. Boom. Le Chateliers Principle states that if a system at equilibrium experiences a change in conditions, the equilibrium will shift in the direction that opposes the change and attempt to restore a new balance. In other words, the system will act to reduce the effect of disturbance. Let's look at the first step of change in concentration. If we increase the concentration of the reactants, the system responds by shifting the equilibrium towards the products, or shifting right. This happens because adding more reactant temporarily increases the rate of the forward reaction. The system shifts to use up the extra reactant and form more products until a new equilibrium is established. Conversely, if we remove some products from the system, the equilibrium will also shift towards the product to replace what has been removed. Now, if instead we remove reactants or add products, the equilibrium will shift towards the reactant. This is the system's attempt to oppose the change by producing more of what was taken away or reducing what was added. In every case, Le Chateliers Principle helps us predict which way the equilibrium will move so that the system partially counters the imposed change. Okay, now let's consider change in pressure or volume. These effects are most important for reactions involving gases. If the total pressure of a gaseous system will shift in the direction that has a fewer moles of gas. This is because reducing the number of gas particles partially counteracts the increase in pressure. If the pressure is decreased, the system shifts in the direction with more moles of gas. However, if the number of moles of gas is the same on both sides of the reaction, pressure changes have no effect on the position of equilibrium. Now, finally, the third major factor that can disturb an equilibrium system is, you guessed it, temperature. Temperature changes are slightly different from concentration and pressure changes because they can change the equilibrium constant itself. We can think of heat as if it were a reactant or a product. If a reaction is endothermic, it absorbs heat. So increasing temperature is like adding a reactant. The system will shift toward the product to use up the extra heat for an exothermic reaction. Heat is released as a product. Increasing temperature adds more of this product, so the system shifts towards the reactants. In each case, the system shifts to oppose the change in temperature. It is also important to understand that not all changes affect the value of the equilibrium constant. Changes in concentration or pressure do not change the equilibrium constant, but changes in temperature do. Removing or adding a catalyst, on the other hand, does not shift the equilibrium position at all. A catalyst speeds up both the forward and reverse reactions equally, helping the system reach equilibrium faster, but not changing where the equilibrium lies. To summarize, Le Chateliers Principle helps us predict the quantitative changes in a chemical equilibrium when conditions are changed. If we alter concentration, pressure, or temperature, we can use this principle to predict whether the equilibrium will shift towards the reactant or towards the products. The system always shifts in the direction that reduces the effect of the disturbance. This powerful idea allows chemists to understand and control chemical reactions in the lab and in the industry. That concludes our lesson on quantitative changes in equilibrium systems. Thank you for watching. Once again, I am Mr. Thomas. Bye-bye.